Well, hello and welcome to my shop, and thank you so much for coming and keeping me company while I work on this radio. Today is September 23rd. It's a gray, rainy day. Quite a change in the weather here. We've gone for, it seems like at least 15 days of beautiful sunny weather, and now it's switched. So, today on this radio, what I intend on doing is start the capacitor replacement process. It may involve just a few capacitors, or it may involve a large number of capacitors being changed in here, like 15 being a large number. And what I'm going to do is I'm going to go after two particular capacitors. This is a stereo receiver, so it has two output tubes, two output circuits, and that output circuit contains a capacitor called a blocking capacitor, whose job it is to keep high voltage away from the grid of the output tube. So we'll take a look at that on the schematic, then we'll try to find them in the radio here. The output tubes are down here. So somewhere in here, we could guess this one, that one, we don't know. We'll try to sort it out with the schematic and identify exactly which two capacitors. We'll then make some tests on the radio operating with the original capacitors. Take out the capacitors, put in new ones, repeat those tests and see what the change is, if any. And with the old capacitors out of the radio, we'll put them through a test also to try to judge the quality and condition of those two capacitors. All that combined should give a pretty good impression about the condition of all the rest of them. And I am really talking about these kind of capacitors here. Those are the ones I'm concerned about being worn out. And when they wear out, what they do is they leak electricity through them. Okay, great. That's what we're doing. Okay, if we take a look at the schematic here, the output stages. One tube here and the other tube here, and the circuit should be extremely similar, if not identical. So if we follow the grid back on one of these tubes, it goes through a fairly small resistor here, and then we encounter this capacitor. This is the one I'm talking about as a blocking capacitor. Now, it's not blocking everything. It has to let the signal through. The signal's being generated or amplified by this tube, and exists on this line here. It passes through the capacitor, this little resistor, and gets on the grid of the tube and then operates the tube. But at the same time, there's high voltage sitting here. Some voltage tube like this, do they say? We can guess it's going to be quite a bit lower than the general B plus in the radio. So 100 volts, 150 volts, that'd be my guess here. We can't afford to have any of that 150 volt pressure get through here and end up in this part of the circuit. What that will do is it will change the bias of this tube. The bias is the operating voltage found between the grid and the cathode. And that voltage typically is a negative voltage somewhere in the range of 10, 20 volts, something like that. And that's to allow a 10 or 20 volt AC signal to fit in the grid without causing the grid to go positive at any point. That's the critical thing. Now, in some radios, the grid is supplied a negative voltage. In other radios, what they do is, instead of making the grid go negative, which is tricky because where's a negative voltage in a radio like this, they'll force the cathode to go positive. And the way you do that, go a little bit positive. And the way you do that is stick a resistor in the cathode line, and there it is. 160 ohm, not a very large resistor, and a half a watt. So it's ready to take some power. Of course, there's power involved in all this because you're trying to drive the speaker out here somewhere, and power is involved. So wouldn't be surprised. There's a heavy current in this, and it doesn't take much resistance to generate that 10, 15, 20 volts right in here. Now, part of the problem here is that this resistor stands between the grid and the cathode, along with these other resistors. So one of the things you want to do is not lose signal across this resistor. So the resistor is bypassed for the signal through this big capacitor. Look, this is a really big one, 50 microfarads. That's a large bypass capacitor. So the alternating current signal, or the signal coming through here, doesn't even know this resistor exists because it's got a highway through here. So another way of looking at that is that from a signal point of view, the cathode is at ground potential. It's not really a good way of looking at it. So these resistors, they work hard, they get hot, they tend to go high. So the 160 becomes 280 or something like that, and the next thing you know, the bias is way off. So that's one thing that can go wrong here, which we will check into. The other one is this guy leaking a little bit of charge. It doesn't take a lot of charge. If you look down here, this resistor is very large. It's almost a megohm. And it's a little hard for the electricity to get through here, so it piles up. The charges coming across pile up in here and start making this more and more positive. So let's say this resistor is producing a bias of 15 volts. That could be nullified by this going up 15 volts, and it'd be at the same voltage. The bias would be gone. The true bias, or functional bias, would be gone. So that's why we can't have a leak here. And it doesn't take much of a leak. Like these capacitors can be slightly deteriorated, this one and this one down here, and this effect can take place. So the test we'll do is first we'll check the voltage. Maybe we'll start here. We'll check the bias voltage. We've got two circuits here to compare, which is kind of fun, although it might be tricky to find all these parts. But we'll try to check this. With the set off, I can actually measure this resistance, which is probably the best thing to do right off the bat. Find it and measure this resistance. While I'm doing that, I'll be in the area of the tube here. I can probably spot this capacitor. Luckily on the schematic they've put the pin numbers, so we can trace, find pin 2, get through the resistor. There will be the capacitor right there. So lots of things can be done here. If you have a leaky blocking capacitor and you're losing grid bias, more and more current flows through the tube. Current doesn't do anything in terms of the speaker. It's a steady state or DC current. But what it does is it wears out the cathode. And if it got really serious, the amount of current would be so high going through here, you might overheat this resistor, or you might overheat the plate from the energy of the electrons striking the plate here. And with kinetic energy, there's so many of them. It's not the speed, but the volume of electrons which could flow through here. And like I said, that's going to deplete or wear out the cathode early. These tubes do tend to have shortened life anyway, because they run hard and they wear out early compared to other tubes, which aren't running nearly as hard. They aren't passing nearly as much current. The cathode is not being consumed nearly as fast. I guess there's somewhat of an ablative effect on the surface of the cathode. That's the story there. Now, just to go a little further, in previous radios I've done exactly what I'm about to do here, and having replaced this capacitor and knowing there's no chance of charge to leak through to here, I still find a positive voltage here. And in the past, I haven't investigated this 100%, but what it probably indicated was the tube was gassy. So that's another possibility. It's not a high likelihood, but it's possible that the tube itself can cause problems if gas has evolved in the tube. And where's this gas come from? There can be gas in the components inside the tube when it's manufactured. Metals pick up gas, and other materials, especially the cathode material, is volatilizing or volatilizing, however you want to say it. And stuff can slowly develop in the tube. I won't go into that in any more detail, but let's just say that there's quite a number of ways for this circuit to fail, and they're all fairly common. Right? Leaky resistor, a leaky capacitor, resistor's gone high, bypass is failing, and the tube itself has trouble. Well, all those different things could happen. Okay, let's just stick with the one here. Yeah, first thing was going to check this resistor, find it and check it. 160 ohms. Let's go looking for it. Okay, so you can see I've got a camera aimed in here, the area of interest. And we get a little closer with this one too. One of the things about these European radios is they layer the components a lot, like things are woven in here. And so accessing some parts that are lower down is very hard, even hard to see them. They're way down there. So that's a bit of a problem. I'm going to remove that clip so we can see a little clearer. So the tube, one of the tubes is right here, and that's the tube socket. And the other tube is right here, and that's its socket. So one of these is a little harder to see than the other. Maybe we should concentrate on this one. And we can look for the resistor. Now another thing about the resistors in here, or a thing about the resistors in here, some of them have the color banding like this one, but others the value is just written on them, and it has to be, you have to be able to see the writing. The last thing is I should know what the pin number is. Let me just take my own peek here. The pin for this resistor we're hunting down is pin number 3, and there's an electrolytic capacitor in parallel with it, so it should be fairly easy to find. Number 3. Let's switch to the other camera. Okay, number 3. Sure. Sure, I can see number 3 there. First of all, no electrolytic capacitor in view that I can see. Let's just pull out a little bit here. Well, there's that big one right there. Oh, and it was a big one, wasn't it? It was a big electrolytic capacitor connected over this way, and then they have that large black resistor right there. That could be the 160 ohm resistor. Let's see if we can find the same components over here. I'd say no, I don't see them. Well, it's a bit of a disappointment. Okay, I thought I was really onto something there. Let's try the pin 3. The pin 3 thing. Now I gotta figure out which one of those pins, you can hardly even tell it's a tube socket. Which one of those pins is number 3? Now I'm gonna benefit by looking with my own eyes, and I get the benefit of stereo vision here. Let's see what we can find out. So I'm looking for the gap, basically. So I believe the gap is right in there. That would make this pin 1, pin 2. This would be pin 3. If that's pin 3, where's the capacitor? It's certainly not this one. This is something else here. This could be the blocking capacitor that I'm going to be looking for. This one down here could be the blocking capacitor. It's a fairly, there's a black resistor right here. That's interesting. Did I start wrong? Did I say there was a gap? There probably isn't a gap where I said there was one. Probably got the numbering totally wrong. The numbers are written right on the socket here, I think. Oh, there's quite clearly a gap right here. This is clearly 1, pin 1, 2, pin 3. Ooh, there's a wire. There's a wire. There's a gray wire. And the gray wire is going all the way up to this terminal you can no longer see. And I'm just going to keep tracing it here. All kinds of stuff off that terminal. That didn't work out so well. Here, terminal. I traced this gray wire, this thing right here. This gray wire goes up to this terminal I'm pointing at. There's a resistor here, looks like 47K written on it. And resistor over here. I don't see any large capacitor in the area except for that one. This one here. This one's 100 microfarads, but the one we're looking for is half that size, 50. What's 100 doing in there anyway? Has something to do with the volume and tone controls or something like that. Well, this hasn't worked out at all, once again. What's with this receiver? That's interesting. You got a nice view in the camera, but with my eyes it's so dark I really couldn't see well in there. So did I get the pin numbers wrong or something? Or did they number these pins differently? Is that possible? I'm looking at the schematic again. Cathode on 3. So cathode resistor on 3, and the bypass capacitor has to be connected there at 50 microfarads. 15 volts, 50 microfarads. 160 half watt. A half watt resistor is a little bit big. What else could we look for? We could look at pin number 7, which should have the... No, let's not do that. Pin number 2 is the grid. Pin number 2 should have a 10K resistor, then after that, the blocking capacitor. Pin number 2 is right beside pin number 3. Okay, let me come back and join you looking at the cam, looking here. And I need a little more light. A little too much for the camera, I guess. So again, we think I was pretty sure where I saw the gap, but I don't feel so sure now. How come? Yeah. Okay, I'm sure. That's a gap right there. What? So this would be pin 2. There's a resistor going to ground here, that makes sense. And off of pin 2 is a capacitor. But I don't see the... there's another resistor supposed to be in here. This is not adding up at all. What? Am I got the wrong tube here? Maybe I've got the wrong tube. I've gone and done something dumb. Oh yeah. Yeah, wrong tube. Okay. Well, that explains a lot. Okay, yeah. So there is the tube I'm after. You can even see it. This thing here. That's one, and the other guy's down here. One down here, one up there, and this is something else. That's why nothing was adding up. Okay. Well, it's good. That's good. You know, that's how you learn. Okay, we'll look at this output tube, and we'll play the same game. I think I see the gap right away. Yeah, the gap is very obvious. So the gap, and then pin number 1 is not connected. Then you see 2, and then we see 3. I'm looking at pin number 3. It's near the top. And what is happening? It's got a wire on it that's going under a resistor to the left there. Let's see if I can point into this. Let me change hands. This is way down here. So this is pin 3 here I'm pointing at. A little wiggly. And yeah, right. What happens after that? So that should go to a resistor, and the resistor should attach to a capacitor, something like this one. Look at the value on this capacitor. It's probably 33. It's probably 0.033, and I think that's exactly the grid capacitor size. Is there another one like this up near the other tube? The only other one like it is way down here. It's back on that tube that confused me. Oh my gosh, okay, just try not to, get too much on your plate at one time, and at least I get overwhelmed when I'm doing this stuff. This is definitely going to overwhelm me. Oh my gosh, how am I going to sort this through here? Holy smokes. Holy smokes. So this resistor appears to be connected to pin 2, not pin 3. Pin 3. So we're looking for a large resistor also in here somewhere. I don't see one. It's a 1/2 watt resistor. Well, there's this thing. Well, look at this. So down here, down here, down this connection, if you follow this wire over, comes to this terminal strip, and then from there it heads off to this big resistor. Now, is this a 160? No. So we don't know offhand if that's a 160, and there's only one of them. Anyway, these things got to be in pairs. Unless I just haven't spotted it. I mean, it can't be too far away. Okay, let's go back to looking at pin 3 here. Pin 3. I'm trying to wiggle things. Yeah. We'll have to do it this way, just by camera work. So that wire comes up. Which one? It's fortunate they've colored all the wires the same way. So it's that very straight one that's pulling straight through. Straight through. Oh my gosh, where is it? Straight through to the other tube? Would be a wire running between the two tubes? On the grid? No. Holy smokes! Out of the pan into the fire. So far, nothing has added up properly here. Now, maybe you're seeing things that I'm missing. I mean, even though it might be on the screen, doesn't mean I'm looking at it. And you might be looking at it. So much for that one. Let's just take a look at this one back in where? Back in here somewhere. This is not it. This is it up in here. You can hardly even tell there's a tube there. Part of that's because it's too dark. So there it is. Deep down underneath everything. Oh, I'm too close for the focus. Okay. Pin 3. Can you spot pin 3 in there? Oh my gosh. I think I see the gap kind of over this way. Oh my gosh, that's just... Huh, okay. You know what I'm going to do? I'm going to stop here. Because, wow, this is... I didn't get anywhere. I didn't find the resistor. I didn't find the capacitor. I found the tube. There's the tube. There's no doubt about it. There it is. No question about it. Wow, I'm going to go take a little break here. Because this is just... nothing's adding up properly. Okay, new approach. I'm going to try to measure the 160 ohm resistor. So right now I'm just checking the clip lead I'm going to use to ground my meter. Yeah, I think they did go to ground, and I think I can just clip her on there. Let's double check. Very good. Okay, pin number 3. Right, let me just double check here because I don't need to be wrong about this. 3 is the cathode. 3 is the cathode. Okay, and Jim, what'd you do with your flashlight? Here it is. Okay, I gotta get down on my hands and knees. I didn't suddenly become shorter. Right? I'm on my hands and knees here. Okay, 3. This is 3. It's not supposed to be 90. 90 ohms. Okay, the other tube. And what I think is pin 3. And good luck making contact with it. Oh my gosh, how can you do it? 90. Well, this enters us directly into the world of I don't have the right schematic. That 90 ohms. Is there another pin with a 90 ohm? There won't be another pin with a 90 ohm resistor. 90 ohms. Both of them showing 90 ohms. Well, it's possible. It's possible. It's possible. I'm going to look at my tube manual here, which gives recommended cathode resistors for different tubes. 6BQ5. Let's see what the book recommends. I don't think it's going to be 90. 6BQ5. 6BQ6? I got something wrong here. What have I got wrong? 6BQ5. It's not in my book. Book is too old. Okay, got a newer one. A less old one. 6. I don't like this book as much. 6BQ5. This book refers you to tables all over the place. 6BQ. There we are. 6BQ5. Let's see. Oh, this doesn't show pin 3 as a cathode at all. Oh, yes it does. Yes it does. Yes it does. Yes it does. Yeah. Okay, that's enough. Yes. Just really wanted to correct that firmly. So we'll come down here and we'll look for under typical operation. We'll just look down here for ohms. There's ohms. That's 38. That's not it. Ohms 4500. That's not it either. Well, maybe they didn't put it in here in this particular one. They push pull. Did they put it down here? Here we are. In push pull cathode bias resistor. Now these tubes are not in push pull arrangement, but this gives you some idea anyway. 130 ohms. So I'm measuring 90, and the book was saying or the schematic. I forgot. The schematic is saying 160, 130, 160, and 90. 90 does seem a little bit low. And what is the B plus for this? For down here and push and pull, there's the plate is up to 300. Well, it's in the same range as 250 here. Same range. What they're doing in this book is they're giving you, the values based on a 250 plate and the values based on a 300 plate voltage. Down here, they don't change much. And so, does it actually give a bias value? Maybe up here. Grid number 1, control grid voltage, minus 7.3. So that's the kind of bias you're looking for. Something like that. The only conclusion I can come to is, because I've seen 90 twice, and you expect these resistors to go high, not low. So a lower reading doesn't mean the resistor is failing. It means that's what it is. Getting two of them with exactly the same reading really says something about the schematic I'm using. The schematic I'm using is for a radio called a 151. This is a 152. How much difference can there be between a 1 and a 2? Can't be that much, can there? Why would it even be any different? There's, Canada, United States, pretty similar. I don't know. I don't get it. Nothing is adding up here properly. So, and where are those capacitors now? Would they have done away with the bypass? Would they have lowered the value of the resistor and then do away with a bypass capacitor? And what that does is it just reduces the efficiency of the tube's ability to produce a strong signal, because you're wasting some of it right in the grid circuit. Could they have done that? They could have done that. I have seen radios with no bypass on the cathode resistor, but usually those are just really cheap. There's nothing cheap about this radio. Cheapers. Well, so what can we conclude from that? That the bias resistor is 90. There's no bypass because they can't find it. That's really a bad conclusion. Let's go for the grid blocking capacitor now, because another measurement we can make is with the set operating, we can go in and measure these bias voltages and see what they really are. So we know they're aiming for minus 7 volts, something, or 7 volts, something like that. So yeah, what pin is the, are we looking at for the grid? I'm looking myself. It's pin number 2, and there should be a 10K resistor followed by the capacitor I'm after, a 33 nanofarad, which is 0.033, I think is the same thing, microfarad. Okay, here we go. There we go. Let's look in the other camera again. It was so helpful last time. It should be helpful this time. Let's elevate it a bit here. I'm standing on the cord. Okay. So we're looking for number 2. The one we tested as number 3 produced a result that I'm now accepting as the correct result. First of all, is that the right tube? Oh yes. Now, where's that gap? So the gap appears to be right here, right here. That's the gap. Pin 1 not used. Pin 2. Is that a resistor? That's a resistor right there. So that resistor appears to connect to this terminal. I mean, where else could it possibly go? Could go anywhere. I think I see the wire coming up and connecting to that terminal, and I'm going to jump to that conclusion because right there is a capacitor, and it's got 33 written on it. So there we are. So this is the grid blocking capacitor. The grid voltage will sit right on this terminal here. Now the other tube should have exactly the same arrangement. So we need another one of these big capacitors. The one I see is down here. But it doesn't seem to be involved at all. This can be quite confusing. It looks like it's connected to this other tube here. This is the wrong tube. This is not one of the output tubes. The output tube's over this way. So, but here's the right size capacitor. It could easily be just grounded here. This could be a handy ground terminal. It's the other end of the capacitor we'd be interested in. So there's where to go. There's the other end. It's ending right here. So we'd want to see a wire. We would want to see a resistor. A resistor going back to the tube socket. That's probably it. I mean, this is a real guessing game. I don't like the guessing part. I really like to be sure of things, and so that's probably the resistor from the grid connection, and then this other resistor we can see right here, which is leaving the terminal, is probably the one that's going down to ground. So that would mean this is one. This is one. This one right here. This is one terminal to test for accidental positive voltage leaking across, and the other one. Wow, this terminal. Oh my gosh, it's really no. It is definitely this terminal here. And the other one to test. Oh my gosh, I've lost track of what I was doing. Be this one. Okay. I think I got it. Ooh, don't forget to hook up a speaker here. Gotta hook a speaker back up. And that's going right on this wire up here. Okay, speakers are connected. Now, I'm going to get all ready here, and then I'm going to take another quick coffee break. Let's get ready though. So this meter's out of the picture. We're just going to get it right out of here. I don't like having piles of stuff on my bench when I'm doing this kind of stuff, because if something starts happening, too much stuff on your bench to sort out. Ground connection. So we're going to use this meter over here because I like it. I like the indicating meter to do this kind of work rather than a meter with numbers on it, because the numbers are actually require more brain power to understand what's happening, whereas the pictorial presentation of the pointer communicates, I think, more powerfully to us visually, as long as you have an idea of, of the scale you're on. And we don't need precision anyway. So I'm going to practice now. So we're going to look for small positive voltage, and I'm going to attempt to get it on the cathode connection and look for the cathode resistor drop, and that's the bias on the tube. So to do that, I would have this set to positive. This would be set pretty low. It's at 50 right now. The set is not on. I'm just practicing, because I'm going to stick this probe in. I better find out now if I can do it. Okay, or if it's crazy to stick a probe in there. So this one I would get this way. That's pretty safe to do, and the other one, oh my gosh, the other one. I'm just trying to spot the gap without doubt. I think I see it without doubt. Okay, that'd be 1, 2, 3. 3, I think. Oh, that's dangerous to go in there and do that. Because there's a term, it's just a tough one to get to without taking too much of a risk here. I think I can do that. And we should see the bias voltage on the tubes. Something like 5 to 10 volts. And then with the set operating, we are then going to want to look for positive voltage on the grid. This meter should do it. It's a less than a megohm to ground, and this is 10 megohm. So we should be able to see, if there's something there, we should be able to see it. Okay, I think I'm ready. Here. Didn't I say I was going to take a break? Yeah, take a break first before you do this, Jeff. Another thing we want to do, or maybe the very first thing, is check the B+ level here, right on the output of the bridge rectifier here. And you can see they've listed it. They've got 3 different voltages listed over here. I'm going to guess it has something to do with what band you're on. As you change bands, some things are changing in the radio, I guess. So the current draw is somewhere between 100 and 120 milliamps. That's quite a change, actually. And the voltages are like 280, about 280. So I should find 280 here if I want to be able to measure the rest of these voltages with any comparative accuracy. What voltages are you talking about? Don't they have the voltages written out here? I thought they did have them written out here. I guess not. I guess not. Thought I saw them. I don't see any voltages out here anywhere. Okay, well, we can guess that this is just going to be slightly lower than the supply voltage back here. Okay, let's check this out. Okay, so the radio is switched to FM right now, which is just fine. Volume is turned just up a wee bit, and voltmeter is set to 500 volts full scale, so we're expecting this to go up just a little past halfway, something like this. That'll be 280. The place we're going to measure it is right on the output of the 2 rectifiers, which is this red wire, I'm sure, right here. We'll test that, read the voltage. We'll know what we're dealing with then, and the next thing then would be to carefully prod the cathode voltages in those 2 tubes on pin 3, pin 2, pin 3, pin 2, cathode on 3, grid on 2. Cathode on 3, grid on 2. Okay. Is everybody ready? I think I'm ready. We're plugged in. Here we go. Okay, dim bulb startup. Of course, we can't have the dim bulbs in when we're doing this kind of work. Let's just watch the B+ come up. So it's already there, 250 volts. Oh, of course it's going to be there quick because it's got it's not dependent on a tube. So we're only running with 80, 84, 83 volts here. Wow, that's way low. And we're still getting it? It's dropping down a bit. Dropping down a bit because we're pulling more current into the radio as the tubes warm up, more voltage dropping on these, less supply voltage, less ultimate B plus voltage. Everything seems okay, so we are now going to switch to full line voltage. We're going to set it here. I can hear the radio playing if we turn it up. So I'm setting this to about 115, that's where I'm aiming. Here we are, 115. I guess the volume came up as I...
You really have to think for that is a woman named Brownie Wong.
Fantastic. So now we're going to look at the B plus voltage with the proper line voltage coming in. And the B plus voltage is... So we're reading, this is a fairly accurate meter. So on here it's 260. You know, that could be 280. That's good enough. So now we want to try to read the cathode voltage. So I'm going to get down on my knees here again. And this. We're going to set this down. 50 volts. So we're expecting this meter to come up in this range. Around here, and then I can make it more sensitive. We'll get a better reading if I care to afterwards. So very carefully now determining 3. I see 3 going in on 3. I can't look at the meter while I'm doing this. I'm touching it. I'm looking. Okay, we're seeing 6 volts. Okay, I'm pulling out. Okay. Touching again. 15 volt scale, that is 6 volts of bias, and we were heading, the book said -7 would be a nice number, so that's pretty close. Okay, now the other tube, I think this is the spot right here. So here we're getting about a little bit, just a touch more, just under 7, but very similar. Okay, so I would say the cathodes are properly biased in this. Now the next step is to try to read the voltage on the grids. It's possible when I touch this, it will bleed off a certain amount of charge or a certain amount of pressure that's in the circuit I'm trying to test. It's going to travel through the meter and be lost. And that may drop the pressure in this part of the circuit. I'm going to get a lower reading than what would really be there if I didn't have the meter connected. In other words, the meter is going to affect the result. The way we can see that is as soon as I touch, the meter can come up and then go back a bit. So it's the come up that's the correct reading, but it will never show us. We'll never know this way. But let's see what happens. Blah, blah, blah. Let's see what happens. And this was pin number 2. Pin number 2. I have to look again at the schematic here. Yeah, that's right. Pin 2. Pin 2 is the grid. I want to get it wrong. Okay, back down on the floor here. Pin number 2. That's right beside pin number 3. Okay, so here we go. First to pin number 2. And when I make contact, I got to be looking. Nothing happens at all. Let's try again. Okay, so I didn't see any movement in the meter. Let's see, make sure we're making contact here. So tiniest movement. Let me put this right down now. 1.5 volts full scale. So you see it's up just a wee bit. So on a 1.5 volt scale, that is all of just over 0.1 volts. Now, what about the other one? I can't imagine. Wait a minute, isn't there? No, I was able to do that test out here, wasn't I? Like right here? Yeah, okay. And I can also do it right here. Oh, look at the other one. Oh, okay, 1.5 volt scale. Still not that much. It's half a volt. Okay, so what this indicates, and I'd be stunned if we didn't find something there, is a leak going through these two blocking capacitors. One of them's a little stronger than the other. The stronger leak is pressurizing the grid circuit a little higher, and we're able to read it. And this didn't seem to bleed away the charge much at all. This is a 10 megohm connection in a 1 megohm circuit, so this is going to bleed away a small percentage of the current. So we should probably get a pretty good reading on it. My meter's gone backwards here. How come? Did I not have this zeroed right? So I'm on positive, so an upscale swing is a positive voltage on the grid relative to the chassis. Let me repeat those now, because it's so easy to do now that I remember how easy it is. So here we're getting 0.65 volts, and the other guy, not quite 0.2 volts. So over time, these capacitors will get weaker and weaker, and in fact, if you let the set operate, especially in the cabinet, the whole set warms up. About every 10-degree increase in heat, you can probably expect a doubling of the leak current through these capacitors. So assuming the whole thing warms up after an hour or so, and maybe much less than that actually, these capacitors could be leaking double, and we could be seeing double the voltages that I'm reading here now. Hard to say. Hard to say if that would happen. But I guess what I'm trying to say is the situation as we're finding it now may get worse as you operate the set over time and it warms up more. So these two capacitors are easy to get at, easy to replace. So I think we should do that. So I'm going to do that. I'm going to replace them, and then when we have these two out, we can test them outside of the radio and find out how leaky they are. I have a device for testing them. Good. Okay, two new capacitors are in. Here's one. Just check it, make sure it's solidly soldered. Yep. And the other one's here. And come on over here where I've got my capacitor tester here. That's this guy. So this is a qualitative test. Okay, it doesn't give any particular measurements, but I've done so many of these tests that I've gotten quite used to what the expected result should be, what good and bad really means. Now, a little bit of a challenge here in the camera is to see the magic eye properly. And it's definitely a challenge here. Let me just drop my camera down. Down, down, down. Get a little closer. So now you can see that there's a pie-shaped dark area here. That's the indicating area. And what will happen is that pie will get smaller or even disappear. The whole thing will be brightly lit like the outside here. So what this guy does is he puts on a DC voltage onto a capacitor. I select the voltage with this control here. Then if there's no current leaking in the capacitor at all, the eye will look pretty much like you see it now. But of course, when I first hit the switch, here's the switch here, there'll be a rush of current to charge the capacitor, even though it's a low voltage setting. That rush of current will be detected or shown in the eye here. The eye will close, and then it will open. Small capacitor, that happens pretty quick. We'll see how far it opens. If there's a leak of any significance, this pie will not open, or not open all the way. So here we go. It says 25 volts here. I doubt you can read it, but it's actually 50 volts. I've tested it. There we go. You see it pop open? That was pretty good. Okay, let's give it 150 volts. Surprising how slow that was, but it's open all the way. This is a 600 volt capacitor. Let's give it 250 volts. Very, very slow charging for such a small capacitor. But the eye is opened all the way, so this actually indicates the capacitor is in pretty good shape. The leak we saw, well, the small positive voltage we saw on the grid could still be coming through here. There's something, I don't think there's anything wrong with it. Once in a while these clip leads don't make a good contact, but it's usually pretty obvious. Let me go back to the 150. No, it's the very same. Very slow to charge though. I don't know what to make of that. It's behaving like a big capacitor. Let's try his brother here. This is the guy who was leaking worse. Or the positive voltage I read was higher. Let's put it that way. We don't really know where that positive voltage has come from for sure. Okay, starting with the 50 volts. Here we go. It's opening right up. So this tells a very good story for all the rest of the capacitors. And part of what I'm doing here is I'm judging all the capacitors in the radio based on these two. So we're at 150, and you can see this guy's not going to open. Or it's just creeping. That's it, half open. So you can see a difference between these two capacitors, one better than the other, and when we took the voltage test, we found one had more, so assumably, leaked pressure in it than the other, and it matches with this capacitor. So everything's adding up. Very, very slight leak. Would this have been harmful to the radio? Well, you're losing a bit of the bias. So this counters the bias. So if you have a leak sufficient to produce, let's say, 1 volt of positive voltage on that grid, on the grid, then it's like having 6 volts instead of 7 coming from the cathode bias. So you lose a little bit. The result of that is heavier current flowing through the tube all the time, and the result of that is a shortened life of the tube. But there's nothing dramatic about these results here. These are actually really good, and this is why this radio works, because it doesn't have a huge pile of sick capacitors in it. That would be what I would conclude at this point. I would also conclude there's no reason to do a general capacitor replacement unless there's an indication of the need, and I'm not sure there's any indication here. So the next thing we need to do is start this guy up again and repeat the cathode tests, or the grid tests, and see if there's a difference. And why don't we just do that? I was going to go for a coffee, but let's just do it. So plug this guy back in. On with the dim bulbs. Anytime I make a change in the radio, especially related to the power supply, this wasn't related to the power supply, but if you do anything that's related to the power supply, dim bulbs are your friend. Okay, so not a particularly good sign. We're not hearing anything. Let's give it the full treatment here. 115 volts. I was a little worried there. Did the radio get retuned, or did the antenna get knocked around, or something happen here? Soldering iron. A little bit of interference from the soldering iron. Here we are.
So then you drink again when you wake up. Like, you know, it becomes such a horrible cycle of things. Yeah.
Yeah, like what happens when you catch the car? Like what happens when you get the thing? That's what I mean. Like you do all that stuff when you catch the car, when you get the thing that you're looking for. And just last thing on this is, you know, at the very beginning you were talking to me a little bit about you growing up loving all these female rappers and growing
Okay, so now, once again, we're listening to the Canadian Broadcasting Corporation, the CBC, the Canadian, I don't want to say government operated, government supported national broadcaster in Canada. Not a similar thing in the United States. Not really. Okay, so here we go. Last time I tested here, we saw this come up to around, I can't remember, I think this one was around here, around this level. Let's see what we get this time. Same thing. So it's lower, but it's there. I don't know if you can't see that, that's for sure. You have to look this way a little bit. Okay, let's try that again. So you're watching this pointer, and I'm going on right here. So it's still a touch of positive voltage, but now we're talking about 0.05 volts. And then we'll go with the other capacitor right here. The same thing. Very, very low. Oop, dropped right off. Just contact. So both of them now very low. The last one, what was coming up to here, now it's only coming up to here. So we will have increased the negative bias on the output tubes and reduced the current. To what degree? I couldn't really tell you. To a significant degree? Probably not. Probably not at this point. Eventually those capacitors were going to leak worse. Now, this thing's already how old? You can imagine how many more years it would take to get that really, really bad off. So the next thing we need to look at is a totally different situation. Because I think I'm going to avoid doing any more of the sort of typical capacitor work, unless there's a strong indication for the need of it. What we need to go after is a very particular capacitor that's involved in the FM discriminator circuit. There's an electrolytic capacitor somewhere in this radio that probably needs to be changed. Probably. So we'll leave it at that. Very good. Looks to me like all this radio is going to require is some alignment work, which I'm a little anxious about too. Just looking ahead, so these are the areas where you make adjustments to do alignment, and I see typically they have waxed these, which means they've set them in the factory and then poured wax into them to freeze them in place. And these ones, you can see the blue colored stuff, that's a paint they put on to freeze that in place, so they don't change ever. So it's a one-time adjustment in the factory at the very end. It's the last thing that happens to the radio, and then it's left alone for the rest of its life. But the rest of its life is only supposed to be 10, 15 years, not 50, 60, whatever it is for this radio. So possibly some of that needs to be adjusted if we want to bring up the function. But frankly, it's working so well, I'm not too excited about making lots of changes to something like this. Too much risk, too little benefit. Okay, well, thanks for watching today, and we'll tune in again tomorrow, see what I've decided to do with this radio. It'll probably be that FM capacitor. Okay, thanks for watching. See ya.